Okay. Now we have got the different category of questions. Let me check it back. Yes. Yeah. This is part B of this question set, in which more than one option can be correct. Okay. So let's see first question. That a battery of EMF E is being charged from a charger such as the positive terminal of battery is connected to terminal A of the charger and negative terminal of battery is connected to terminal B of the charger. Okay, so there is a charger, definitely it's a battery also, and there is one battery which is being charged. Okay, the internal resistance of battery is R, EMF is E. Its positive terminal connected to terminal A and negative terminal is connected to terminal B. So definitely current is coming from this. When charging takes place, then current move towards the battery. Now options are: the potential difference across point AB, across this point, must be greater than E. So this statement is correct, because only when VAB is greater than E, then current will move from terminal A towards battery. So option is correct. A must be at higher potential than B. It is also right. That's why we are getting current in this direction from A to B. Next, in battery, current flows from positive terminal to negative terminal. Definitely, when charging process would take place, then this current move from positive terminal to negative terminal. So it is correct. T is no current flows through the battery. It is not right. So option A, B and C are correct in this question. Okay, let's see next one. A battery of EMF E and internal resistance R is connected across a resistance R. R can be adjusted to any value greater than or equals to 0. A graph is plotted between the current passing through the resistance and potential difference across the resistance. It selects the correct alternative. Okay, so here we can see, as current is increasing, the potential difference is decreasing. Okay, and it finally reduces to 0. Okay, so basically which process is taking place? There is a battery with certain internal resistance and a resistance R is connected in parallel. Okay, so whenever this circuit is closed, then due to current there is drop in terminal potential of the cell. Okay, and which appears across resistance R, as terminal potential V is equals to E minus IR. Okay, and which is potential across this resistance. So from this graph we can write the equation. This is intercept form of graph. Okay, so in the equation in intercept form is x upon a plus y upon b is equals to 1. Similarly, we can write v upon 10 plus I upon 2 is equals to 1. So it will give us that v plus 5I is equals to 10, or we can say v equals to 10 minus 5 into I. If we compare with this terminal potential equation to the equation of this line, then we can say that EMF of this cell is 10 volt and internal resistance of cell is 5 ohm. Right. Now we can go through the option. First is internal resistance of battery is 5 ohm. We already calculated this. It is right. Next, EMF of the battery is 20 volt. This is not the same, so it is not correct. Option C, maximum current which can be taken from the battery is 4 ampere. It is also not correct, right? Because the maximum current which can be taken out from the battery is, if we'll take this value is equals to 0, then I is equals to 2 ampere, or from this graph it is visible, so it is not correct. Next, VI graph can never be a straight line as shown in figure. So definitely it is not correct. Okay, this is violation of basic Ohm's law. So only option A is right in this question. Okay, next question is, the equivalent resistance of a group of resistance is R. If another resistance is connected in parallel to the group of resistance, then new resistance becomes R1. If this resistance is connected to the group of resistance, then new resistance becomes R2. So suppose we have a group of resistance, can be anything. Suppose this is our combination, and for that we are getting an equivalent resistance R. Now the question is saying that if we'll connect one resistance in parallel, then new resistance is R1. On the other hand, instead of this one, we connect an resistance in series, then new resistance is R2. Okay, so look, we can do some prior exercise. That whenever we connect resistances in parallel, okay, then net resistance will always be less than total resistance involved in the circuit. Okay, like let me show you an example. That suppose if it is a 10 ohm resistance and another is 5 ohm resistance. Okay, so net resistance would be 50 divided by 15. So that is 3 point something. Okay, so in parallel combination, net resistance is always smaller than the smallest one. So we can say that R1 will be smaller than total resistance R. On the other hand, if we connect a resistance in series, doesn't matter what value, then net value whatever we'll get will be greater than all resistance involved in this circuit. So we can say R2 is greater than R, right? Or we can say R2 is greater than R1. So let's see the option. First, R1 is greater than R. It is not right. R1 is less than R. Correct. R2 is greater than R. Correct. R2 is less than R. It is not right. So option B and C are correct for this question. Next, two identical fuses are rated at 10 ampere if they are joined. First, in parallel combination, it acts as a fuse of rating 20 ampere. So definitely when we connect two branches in parallel, okay, then current get divided, right? I equals to I1 plus I2. So one fuse can sustain 10 ampere current. So if we are connecting them in parallel, then in combine they can sustain 20 ampere of current. So option A is correct here. Next, in parallel the combination act as a fuse of rating 5 ampere. It is not correct. Next, in series the combination act as a fuse of rating 10 ampere. So definitely if we'll connect them in series, then current remains same in series. and they can tolerate only 10 ampere current. Okay. So in series combination doesn't matter how many fuses are connected, but the overall rating would remain same. So option C is correct. Option D, in series combination, the combination act as fuse of rating 20, which is not right. So in this question, option A and C are correct. Okay. Now, two circuits are called circuit A and circuit B. The equivalent resistance of circuit A and circuit B. Circuit A resistance is X and circuit B resistance is Y. Okay. So here we can see this is infinite combination of infinite resistance here. Right. So in infinite resistance, doesn't matter from which point we are looking. Okay, we'll get similar equivalent resistance. So resistance of this portion is X as well as resistance of this portion is also X. So we can draw a reduced circuit that suppose these are terminal 1 and 2. Resistance from here is X, which is connected through R and 2R, which is finally connected across resistance X. Similarly for circuit 2, we can divide two sections from here. Suppose this resistance is Y and this is also Y. So here we are just taking a advantage of infinite series, that if you break a link from there, then there will be no effect on entire resistance, right? So we can draw equivalent circuit for figure 2 like this. Y. So we can write net resistance. So from here we will write X is equals to R parallel with 2R plus X, which is equals to R into 2R plus X divided by 3R plus X. So from here we'll get 3Rx plus X square, which is equals to 2R square plus Rx. Okay, so it is X square plus 2Rx minus 2R square, which is equals to 0. Okay. To R square plus Rx, right? So from here we can calculate X. X is minus B, so minus 2R plus minus under root B square. Okay, B square is that is 4R square plus 4AC, that is 8R square upon 2A 2. So from here we'll get X is equals to, this is 8R square, so we can take 4R square common, so this is 2R root 3. Okay, so from here we'll get root 3 minus 2 upon 2 root 3 minus 2 upon 2 into R, that is root 3 minus 1 into R, value of X. Similarly we can calculate value of Y. Value of Y is 2R in series with parallel combination of R and Y, right? So this is 2R plus R into Y upon r plus y. So from here we can write ry plus y square is equals to 2r square plus 2ry plus ry. So this will give us y square minus 2ry minus 2r square is equals to 0. Okay, so from here we'll get y equals to 2r plus minus under root 4r square plus 8r square upon 2. So we are getting almost similar equation, only difference is one sign. So y is equals to root 3 plus 1 into r. Okay, now let's look at the options. First, x is root 3 minus 1 and y is root 3 plus 1. So definitely y is greater than x, so this option is right. Second, y is root 3 plus r, so this option is also correct. Third is xy equals to 2r square. So if we'll multiply x and y, so we'll get root 3 minus 1 into r, root 3 plus 1 into r. So this is a minus b into a plus b, that is root 3 square minus 1 into r square. So this is 2r square. So this option is also correct. Next is x minus y is equals to 2r. So we will subtract x minus y, then minus root 3 we cancel and we'll get minus 2r. Right. So it means this option is not correct. So in this question, option A, B and C are correct. Okay, let's see next question. Question number 6. The value of resistance R in this figure is adjusted such that power dissipating 2 ohm resistor is maximum under this condition. So see, resistance power drop across any resistance is I square into R. This power would be maximum when I is maximum. Okay. So when we'll get the maximum current passing through any circuit. Okay. When this circuit will have the maximum current. Whenever the total resistance of this circuit is minimum, then we'll get maximum current in this circuit. Okay. So when this R net will be minimum. Yes, R net will be minimum if this combination reduced to 0. Right. And when this combination can reduce to 0? If you short circuit this element. Right. And for that purpose, R must be equals to 0. Okay, so if we'll put R equals to 0, then this parallel combination will offer no resistance and maximum current will pass through this circuit, and in result of that we shall get maximum power dissipation across 2 ohm resistance. Second, if R is equals to 8 ohm, so it is not right. Third, power dissipated in 2 ohm resistor is 72 watt. So if this combination having no resistance, then current passing through this circuit would be I equals to 12 upon 2, that is 6 ampere. So power would be 6 square into 2, so that is 72 watt. This is right. So option A and C are correct for this question. Let's see next question. Question number 7. A galvanometer may be converted into ammeter or a voltmeter. In which of the following cases the resistance of this device would be largest? So whenever we convert any galvanometer, okay, in ammeter or voltmeter, okay, so we always try to get maximum current for this element, okay, if we are converting into ammeter, and we want least current through this element if we want to convert in voltmeter. So in case of voltmeter, we convert a high resistance in series, and in ammeter we connect a very least resistance in shunt. Okay, so it means when we convert this galvanometer in a higher range of voltmeter, then we require very high resistance, right? So first ammeter of 10 ampere range, so we need less resistance. In this we also need resistance. Okay, so as compared to 5 volt rating voltmeter, 10 volt required large resistance. So option D is correct in this question. Next, question number 8. Mark out correct option. An ammeter should have a small resistance, it is right. A small shunt resistance should be there. An ammeter should have large resistance, it is not correct. A voltmeter should have a small resistance, it is not right. There must be a large series resistance. So option A and D are correct. Now question number 9. In the circuit shown in figure, the reading of ammeter and voltmeter are 4 and 20 amperes. Okay. The meter are non-ideal, then R is. Okay. So please see, here one ammeter is connected in series and it is providing rating of 4 ampere reading here. It means current passing through this resistance is 4 ampere. Another voltmeter is connected in parallel, that's showing reading of 20 volt. Right. It means the potential difference across this resistance is 20 volt. So we know V equals to I into R, basic Ohm's law. So from here we'll get R is equals to V upon I. That is 20 divided by 4. So from here we are getting 5 ohm resistance. Okay. But these voltmeters and ammeters are non-ideal. It means they are showing the available value less than what was the actual value. So the resistance would not be exactly equals to 5 ohm. Its value must be a bit higher than this, because they will not show the correct reading. So option C is right. Now question number 10. A micrometer of resistance 100 ohm and a full scale range is 50 microampere. It can be used as a voltmeter or a higher range ammeter provided a resistance is added to it. Pick up the current range of the resistance in these combinations. So basically what is given right now, that there is a micrometer which is showing full scale current is 50 microampere. Okay, and the internal resistance of this micrometer is 100 ohm. So if we want to convert this micrometer meter in an emitter, okay, like of 55 milliampere or 10 milliampere, whatever we want to convert it, then definitely we need to connect a shunt resistance in parallel so that it can take out the extra amount of current. Like if I current is coming from here, so this meter can take only 50 microampere current. So additional current must pass through this resistance I extra. But they are connected in parallel, then they must hold same amount of voltage. Okay, so we can say that I extra into resistance connected in parallel must be equals to 50 into 10 to power minus 6 into 100, that is 0.005. Okay, so I extra we are creating a 55 milliampere ammeter, for example. Okay, so 5 milliampere means in microamperes we can write 500 microampere. Okay, in fact 5000 microampere. Okay. So the extra current passing through this element would be 5000 minus 50. Okay. So this is 5000 minus 50. So we'll get 4950. Yes. So this is 4950 into R. Right. So from here we can calculate value of R. Okay. And this current is microamperes. We must keep in mind that this is 4950 microampere. Okay. And this is in volt. So we can say R is equals to approximately 0.005 divided by 0.0049. Okay, so it means it is approximately equals to 1 ohm. So option C is right for sure. Similarly, if we'll take 10 milliampere off range, then again we use same procedure, and here you can, by solving, you may get that it will not be equals to 1 kilo ohm. Okay, now next, if we want to convert this element in voltmeter, so this combination of micrometer and the resistance can tolerate only 0.005 volt only. If we want to increase its range, then we need to connect a higher resistance in series that can tolerate extra voltage, keeping the condition that the current in this circuit would remain same because we are connecting a micrometer in series and current remains same in series. Right. So suppose if we want to create a 10 volt voltmeter, okay, then the total potential, that is 0.005 across the micrometer plus current through micrometer, which is 50 into 10 to power minus 6 into the resistance connected in series, this must serve our purpose of 10 volt. Okay, this total voltage can be distributed in two parts. Okay, so from here we'll get 50 into 10 to power minus 6 into R, which is equals to 10 minus 0.005, which is 9.995. Okay, so from here it will calculate R, then we'll get approximately 200 kilo. So option B is also right. We will apply same procedure for this 50 volt, so it would not be right. Okay, so simple procedure is you can calculate extra resistance which is connected in parallel for ammeter and extra resistance in series which is connected to convert it in voltmeter. Now next is question number 11. A potentiometer arrangement, E cell is establishing primary current. E2 is the cell to be measured. AB is potentiometer of wire. G is a galvanometer. Which of the following essential condition for a balance to be obtained? So basically, if we have a potentiometer wire AB, okay, then E1 is cell to establish primary current. So we must connect a cell E1 here, which is establishing the primary current. Now E2 must be connected at terminal A and followed by a galvanometer to get the balance condition. So first question is, EMF E1 must be greater than EMF of E2. It is right, because only when E1 is greater than E2, it can develop a potential difference across AB that can be measured through K into X into E2, and where K into X is E over L, which is length of wire, into E2. Okay, so E1 must be greater than E2. It is right. Next is, either the positive terminal of both E1, E2 or the negative terminal of both E1, E2 must join to one end of the potentiometer. This is also correct, because we need to develop same polarity across the galvanometer. That's why we'll get the zero deflection. So the polarity connected to the terminal A of the potentiometer must remain same. So it is correct. Next, the positive terminal of E1 and E2 must be joined to the one end of potentiometer wire. So it is again saying the same statement, that both ends must be joined. The potential positive terminals of E1 and E2 must be joined at one end of the potentiometer wire. No, it is not necessary. Okay, like in this case you can see the positive terminals are not joined at similar end. Here we are getting the negative terminal. Although we can get the same measurement by connecting the positive terminal at same point, but here it is using must be joined, which is not always true. Next, the resistance of G must be less than the resistance of AB. There is no condition on the resistance of galvanometer, because it will maintain a constant potential difference across the terminals of G, then resistance would not matter. So option A and B are correct. Next, question number 12. A potentiometer wire experiment. EMF of primary battery is 20 volt and its internal resistance is 5 ohm. There is a resistance box in series with the battery and potentiometer wire, whose resistance can vary from 120 to 170. Okay. The resistance of potentiometer wire is 75. Then the following potential differences can be measured into using the potentiometer. Right. So there is a cell of 20 volt. Internal resistance of this cell is 5 ohm. There is one resistance box that can offer resistance from 120 to 170 ohm. And in series with this, there is a wire of potentiometer which can offer a resistance of 75 ohm. So here when we have to decide that which value of EMF it can measure, then we need to look at the possibility of maximum voltage. So how much maximum potential difference we can develop across it. Okay, we can develop the maximum potential difference by minimizing the current coming out from the cell. Right, that's why we'll get the minimum terminal potential across it. Okay, so first we need to measure I minimum. What is the minimum current? So I will be minimum when this resistance would be maximum across this terminal, right? So maximum resistance can be 175 plus 170 plus 5. Oh, sorry, 75 plus 175, that is 250. So current coming out from this is 20 divided by 250, that is 0.08 ampere. So we can check the potential difference across this cell. One second, I think this is wrong assumption, because the terminal potential across this resistance AB, the wire of potentiometer, would be EMF of the cell minus I into 5 ohm internal resistance plus resistance of box. So if we want to increase this reading, then we have to take it minimum. Then only we can measure the maximum voltage, because this resistance also needs to be included for the calculation of terminal potential, right? So let's take our box minimum value, that is 120. So what would be the current? EMF divided by total resistance, that is resistance of cell plus resistance of box plus resistance of wire. So from here we'll get 0.1 ampere. Then potential which can be developed across this resistor wire AB is 20 minus 0.1 into 5 plus 120. So this is 20 minus 12.5, that is 7.5 volt. Okay, so maximum voltage that we can develop across the terminals of wire AB by using the minimum resistance of resistance box would be 7.5 volt. So it can measure any value which is smaller than 7.5. So it can measure 5, it can measure 6, it can measure 7. So option A, B and C are right for this question. Okay, let's see next question. Question number 13. In given potentiometer circuit, the resistance of potentiometer wire AB is R0. C is the cell of internal resistance R and G is the galvanometer. Does not give zero deflection from any position of jockey. Which of the following cannot be region for this? So please see. If any cell is not giving zero deflection for any position of jockey, it means one thing is sure, that EMF of cell C is greater than terminal potential of AB. Okay, this is the main region. But in this question it is asking which of the following cannot be the reason. Okay, first R is greater than R0. So definitely the internal resistance of this cell does not matter as far as zero deflection is concerned, because if potential across terminals of galvanometer are same, then there will be no current in this circuit. Okay, and if there is no current, then this R will not play its role. So whenever we use potentiometer, the internal resistance of second cell does not matter. So this option is right. It is not a proper region for zero deflection. Let's check other options. R is very much greater than R0. Okay, where R naught is the resistance of this wire AB. So if internal resistance of cell is very much greater than the resistance of wire, then definitely it will reduce the terminal potential and the full scale of your potentiometer decreases. Okay, so it is a region, but here we need to find which is not a region. EMF of C is greater than D. We have already seen this, so it is also a valid region. Next, the negative terminal of C is connected to A. It is also a valid reason because same polarity must be connected at point A. So these are three valid regions. Due to that we can get this problem, but first option is not valid. So we'll go for option A. Okay, next question. Which of the following quantities do not change when resistance connected to a battery is heated due to the current? Okay. So when we heat the resistance, then definitely its drift speed changes, because in expression of drift speed we get the temperature. Resistivity also a temperature dependent quantity, that is rho naught 1 plus alpha delta T, and resistance is also proportional to resistivity, so it will also change. But here we have to find out which do not change. So number of free electron never changes with the change in temperature, only their speed increases. So option D is correct for this question. These options are not right. Okay, now question number 15. A metallic conductor of irregular cross section shown in figure. The constant potential difference applied across point A and B. Okay, now we have to choose correct answers out of these. First option is the current in cross section P is equals to current in cross section Q. So if your wire is same, that is subjected to a common potential, then current remains same in series. So current all pointed would remain at all points would remain same, means option A is correct. Next, the electric field intensity at P is less than the electric field intensity at Q. So definitely electric field intensity is depends on the potential difference and distance from higher potential point. E equals to delta V over T, or we can say E equals to minus E dot TR. So it depends on the distance from point of higher potential. So this option is also right. Now the rate of heat generated per unit time at Q is greater than heat generated at point P. So here we can see that rate of heat generated delta H over delta T is proportional to I square into R. But current remains same, so it depends on resistance. And resistance is a parameter that depends on physical dimension. So point where cross-sectional area is smaller would offer higher resistance. Okay, so it means in this region resistance should be greater, so there will be higher rate of heat generated. Okay, so this option is also right. Next, the number of electron crossing per unit area of cross section at point P is less than that of point Q. So as if current remains same, then I equals to NEAVD. Okay. So if your cross-sectional area is smaller, then the drift velocity would be higher in this region, and drift velocity would be smaller in this region because area is greater. Okay. So it means the number of electron crossing per unit area of the cross-section at point P must be less than at point Q. So all 4 options are correct in this question. The conductor is made of isotropic material, has shape of truncated cone. A battery of a constant EMF connected across it. The left end is earthed as shown in figure. If section X from left end, the electric field intensity, potential and the rate of generation of heat per unit area is E, V and H respectively. So which of the following graphs are correct? Okay. So here we can see there is a cone which is truncated one. It means cross-sectional area is changing. Now it is subjected to a common potential. Right. So there will be definitely an electric field inside it. We can write J equals to sigma into E, which is conductivity of this material. Right. If at any distance where cross-section is R, cross-sectional radius is R, then this J can be written as I over pi R square, which is sigma into E. Right. So at any distance R, or we can say X, your electric field is inversely proportional to X square. Right. It means this option is not right, at least. Option A is not correct. Now next is power. Power is equals to, here we can say that power at any point, okay, V equals to I into R. Okay, before power we can check out the voltage. V equals to I into R, and resistance R is rho into L. Suppose we are moving this distance L, into pi X square. Right. And power is equals to I square into R. So at any point, power is also proportional to 1 over R. Okay. And heat is dP over dx. Right. So if power is inversely proportional, or we can say any constant over x, and heat is dP over dx. Okay. So it means we'll get this graph for the heat. So this option is definitely correct. Okay. And second, this one is heat versus electric field. Okay. So as we are moving from broader section, electric field is decreasing. Along with that, heat dissipation is also decreasing. Okay. So from here we can say that heat is proportional to the electric field. Okay. So it means we are getting a straight line. So option B and C are correct. Okay. And as far as potential difference is concerned, potential difference if electric field is decreasing, right? So potential difference will definitely increases when we move from one terminal to another terminal, right? So this option is not right. So option B and C are correct in this question. Next is question number 17. A simple circuit contains an ideal battery and a resistance R. If second resistance is placed in parallel with the first resistance, Then the potential across R will decrease. Second, the current through R will decrease. Third, the current delivered by the battery will increase. Fourth, the power dissipated in R will increase. So basically we have a battery which is ideal one. There is one resistance R initially. Now second resistance is parallel with respect to first R2. So we know very well that as this battery is ideal, then potential across this resistance should be V, because total potential should be 0 in a closed circuit. If we'll connect anything in parallel, okay, then the voltage remains same in parallel. So there will be no change in potential difference across R. Second thing, when we connect two resistors in parallel, then R net would be smaller than the initial resistance. And if total resistance of circuit is decreasing, then net current must be increased and it must be greater than the previous one. So this option is not also wrong. Next, the current delivered by the battery will increase. So if total resistance is less, then definitely current delivered by the circuit will increase. Power dissipated by R will be increased. Okay, so the potential difference remains same across these elements, right? And total voltage also remains same. So power dissipated is V square over R. Okay, V square over R net, I must say. If R net is less, then definitely total power dissipated must be increased. So option D is also right. But in this question there is a small doubt that it is asking about resistance R only or the total combination. Okay, because if it is asking about R only, then potential difference remains same, then there will be no change in power dissipation. Okay, so if we go by the language of this question, then this option must be wrong. If we'll talk about total power dissipation, then that will definitely increase. But if we take resistance R only, then there will be same power dissipation. Next question. In this circuit shown, E, F, G, H are the cells of EMF 2, 1, 3 and 1 respectively. Their resistances are 2, 1, 3 and 1 in same order respectively. Then we have to answer these questions. VD minus VB is 2 minus over 13 volt. VD minus VB. It means we want to measure potential difference across it. VD minus VB. Okay. Right. So we can just do a very simple thing. Let's analyze this circuit. Suppose this terminal is grounded. We are taking temporarily this terminal grounded and this terminal as VD. Okay. Suppose one current I1 is coming from there, I2 is coming from there, and I3 is moving in this circuit. Right. So I1 plus I2 must be equals to I3. Now what is I1? Potential difference in this branch as two cells are connected in opposite polarity is 2 minus 1 along the direction of current. So this is 1 minus VD divided by total resistance 3 plus. Again there are two cells are connected in opposite polarity and along the current it is 1 minus 3, that is minus 2 minus VD divided by total resistance 4, which is equals to VD minus VB, which we can take 0 or whatever we want. So let's take 0 here, and resistance is 2 ohm. Okay. So if we'll calculate VD from here, then what we are going to get, that 4 minus 4 VD plus or minus 6 minus 3 VD is equals to 6 VD, right? So from here we'll get 13 VD is equals to minus 2. It means VD is equals to minus 2 by 13, right? So the potential difference between VD minus VB is definitely minus 2 by 13. So option A is right. Next, VD minus VB is equals to 2 by 13. So both can't be right. So it is not correct. Next, VV. The potential difference across G, across this cell, is minus 21 by 13. So look, if we have VD, that is minus 2 by 13, so we can calculate current I1, which is going through this cell, or current I2. So current I2 is minus 2 minus VD over 4. So we can write current I2 with this direction respectively, that is minus 2 by 13 divided by 4, right? So this is minus 24 upon minus 28 upon 13 divided by 5. So this is minus 7 by 13 I2. So if we'll calculate voltage across VG, so this VG is 3, the potential of the cell, and current is moving towards the cell as per our assumption. So this is plus sign into minus 7 by 13 into the internal resistance, which is 3. So this is 21 by 13. So from here we'll get 39 minus 21 by 13. So this is minus 18 by 13. Right. The potential across cell G. The potential difference across G. So current is 7 by 13 and this is 3. Okay, so we just want to measure potential difference across this point, I think. Then we'll definitely get minus 21 by 13. We don't have to find the terminal potential here. Right, so this option is correct. Now next is the potential difference across cell H. VH we have to calculate. So I1 is 1 minus VD by 3. So this is 1 minus plus 2 by 13 by 3. So this is 15 by 13 into 3. From here we'll get 5 over 13. Okay, now for cell H, the internal resistance is 1 ohm. So this is potential difference is 5 by 13. Okay. And its internal resistance, I think we have to try this question again from this point itself. Let's look at this question again. Suppose current I1 passing in this loop and current I2 is passing in this loop. Okay, so if we'll write KVL equation in loop number 1. So from here we'll get minus I1 into 1 into plus 1 for this combination. Okay. In second combination, minus 3 into I1 minus 3 volt across G minus 2 into I1 plus I2, which is equals to 0. Okay, so from this equation, we need to keep these 2 points. Okay, from this equation, we can rewrite again. So this is minus I1 minus 2I1, so that is 3I1, and similarly minus 2I2 is equals to plus 2I2 will be there, is equals to minus 3 and plus 1, so that is minus 2. This is our first equation. Similarly, we'll write for second loop. So this is minus 2I2 plus 2, okay, minus I2 minus 1 minus 2I1 plus I2 is equals to 0. Right. So from here we'll get minus 4I2, that is 4I2 and plus 2I1, which is equals to 2 minus 1, that is 1, equation number 2. Okay. So if we'll multiply in this equation by 2 and subtract from equation number 1, right. So from here we'll get, or subtract equation number 1, I am writing 1 into 2 minus equation number 2. Right. So from here we'll get 6I1 minus 2I1, that is 4I1. I2 will be neglected because this is cancelled out. Minus 4 minus 1, which is minus 5. So I1 is minus 5 by 4. Now by substituting in any equation we can calculate I2. That I2 is equals to minus 2 minus 3 into minus 5 by 4 and total divided by 2. So this is minus 15 minus minus plus 15 minus 8, that is 7. So minus 7 by 8. This is I2. Plus 7 by 8. Yeah, plus 7 by 8. So I1 and I2 are known. Now the potential difference across BD is 2I1 plus I2. Okay. So that is 2 into I1 is minus 5 by 4 and I2 is 7 by 8. Okay. So this is eight minus 10, 7. Look at this question again. That in this question a circuit is given that comprises of 2 ohm resistance in the middle and 4 batteries as shown in figure. So here we assume that suppose current I1 is coming out from this branch. This is our current I1. Current I2 is going through this branch and current I3 in this. Right. And suppose potential of this terminal is VD and this one is grounded. So if we'll apply Kirchhoff's current law, so 2 currents are One current is coming towards node, that is I1, and two currents are outgoing, that is I2 plus I3. So current I1 would be total potential difference in this branch, that is potential of cell A minus potential of cell B, cell F. So this is plus 2 and this is minus 1. So the potential difference across this terminal is 1 minus VD divided by the total resistance of this branch, that is 3. It must be equals to VD minus 0 by 2 plus VD minus the potential difference of this branch. Okay, so the potential difference would be minus 3 for this cell which is connected in opposite and 1 for this. So this is VD minus 2 divided by the total resistance which is 4. So from here we'll get 4 minus 4 VD which is equals to 6 VD plus 3 VD plus 6. Okay. So from here we'll get 13 VD is equals to minus 2. So VD is equals to minus 2 by 13. It means VD minus VB is equals to minus 2 by 13. Okay. Now next, if we'll calculate current I2 as shown in this figure, then I2 is equals to VD minus 2 by 4. So this is minus 2 by 13 divided by plus 2 minus 2, so plus 2 divided by 4. So from here we'll get minus 24, okay, divided by 4 into 13. So this current is minus 6 by 13. Okay. So if we'll calculate potential across G, VG. So current is coming out of this. So this is EMF of G minus I2 into resistance of G. EMF of G is 3 minus resistance of G is also 3 into minus 6 upon 13. Okay. So this is 3 minus and minus plus, so 3 plus 18 upon 13. So VG is 39 plus 16, that is 55 upon 13. Similarly, we can calculate VH. VH is potential of cell plus I2 into resistance of cell, right? So potential of cell is 1 minus I2 is minus 6 by 13 into 1. So from here we'll get minus 19 by 13 for VH. Okay. So in this option we got VH 19 by 13 and second VD minus VB is minus 2 by 13. Right. So in question number 18, option A and option D are correct. Again, we are getting same calculation error in VG, which is 21 upon 13. So we have to recheck our calculation once again, that VG is 3 and let me check it again, that VG is 3 okay, Eg I must say, it is 3, and current is coming towards cell, so this is 3 minus this current minus 6 upon 13 into internal resistance of 13. Okay, so this is 39 plus 21. Okay, so definitely there is some printing error. So option A and D are correct as per my calculation, and if definitely take the different orientation of cell, then we are getting 21 by 13 as well. Okay, so please recheck calculation once. A current passes through a wire of non-uniform cross-section. Which of the following quantities are independent of cross-section? So, if we have any wire having variable cross-section, then we need to select that which parameters are not depending on that. First, irrespective to the cross-section or resistance offered by a conductor, current remains same. It means dq over dt would remain constant. So the charge crossing in a given time interval would remain constant. Number 1. Current density depends on area, so it is not correct. Drift speed also depends on area, it's not correct. Next, free electron density. It depends on nature of the material, and irrespective to its cross-sectional area, the free electron density would remain same. So in this question, option A and D are right. Okay. Now there is combined statement from question number 21 to 24. The figure shows a network of resistance and battery. If 1 ampere current flows through branch CF, then the answer the following question. So please see. Here branch CFD, this one, CDEF, is parallel to branch CF, and this branch having resistance 2, CF having resistance 2. So whenever they get powered by a common source, then total incoming current must be equally divided between them. It means current passing through these elements is 1 ampere, and total current coming to this terminal is 1 plus 1, 2 ampere according to Kirchhoff's current law. Right. Now, here net resistance of this combination, if we look at from between terminal B and G, one resistance is 6 ohm, another resistance is 2 and 2 parallel to 1 and 2. So there is 3. Okay. So it means the ratio of current between these two is 2:1, because one resistance is 3 ohm, another is of 6 ohm. So if there is 2 ampere current passing, so in this element current would be 1 ampere. So total current coming out from the battery is of 3 ampere. Right. And total resistance of this network is 6 and 3 are in parallel. That is 6 into 3 divided by 6 plus 3. So 2 ohm. Finally, we can reduce this circuit as a combination of a cell with 4 ohm resistance. So total resistance is 4 ohm, total current is 3 ampere. It means the EMF of this cell is 12 volt. Now we can answer all these questions. First, the current through branch DE is 1 ampere. It is right because DE in series with this. It means option A is correct. Next, in branch BC is 2 ampere. So we can see here, after applying KCL, the current in branch BC is 2 ampere. Branch BG is 4 ampere. It is not right. Branch HG is 6 ampere. It is also not correct. So it means option A and B are correct in question number 21. Next, EMF of cell we already calculated that it is 12 volt. So option B is correct for question number 22. Next, if the zero resistance wire is connected in parallel to CF, here we are connecting a zero resistance wire. Okay, so zero resistance wire means short circuit. So whenever we connect any resistance in short circuit, then it just diminishes the effect of all resistance in parallel, right? So total current will pass through this branch only. So after connecting a short circuit in parallel, our equivalent circuit would be like this. Now this is a 12 volt battery. So now we can check in this question that the current through branch DE is 0, right? Because total current will pass through this short circuit. So this option is correct. Branch BC, B and C is 0. It is not correct. Because if you connect something in parallel, then it will affect. But if there is connection in series, there will be no effect on current. Now next, EMF of E of the battery is EMF E of the battery is 12 volt. We already calculated because there is no effect on EMF of the cell due to short circuit. Okay. Next question. Inside a superconducting ring, identical resistance each of resistor are connected as shown in figure. So there are 6 resistance and these 6 resistance are connected through superconducting ring. Okay, and superconducting rings mean these rings will offer resistance between point 1 to 2, 2 to 3 and 3 to 4. Okay. So net resistance between these elements, these points is 0. So we can draw a reduced circuit for this combination. That there would be no effect on these resistance. So, point 1, point 2 and point 3. And between these points we can replace zero resistance. So again, zero resistance means short circuit. It means if you look taking point O as a reference, then point 1, 2, 3 are basically connected at same point because they are short circuit and each having resistance R. So net resistance between O1, O2, O3 will be R by 3. Now we can easily answer these questions. First, between 1 and 3 is 0 resistance. So definitely we'll look between point 1 and point 3. So it is short circuited, so net resistance is 0. Next, 1 and 3 is R by 2, it is not right. Between 1, 2, 2, 3 and 3, 1 are equal. So 1 and 2 are short circuited, 2 and 3 are short circuited, and 3 and 1 are short circuited. So they all terminals will offer equal potential, hence net resistance between them will be 0. Right. So this option is right and D is not correct. Next, the equivalent resistances between 0 and 1 is R. We already calculated. Between 0, 1 and 1, 1 and 0 and 2 and 0 and 3 is R by 3. So option B is right here. And third option D is correct because between 0 to 1, 0 to 2 and 0 to 3 all are equal. Next, imagine a battery of EMF E between point 0 and 1 with the positive terminal connected to. So in this circuit, it will connect a battery between 0 to 1 whether positive terminal is connected to. Okay. Then we have to answer these questions. First, the current entering O is equally divided in three resistances. So here we can see across point O there is three symmetric resistance. Okay, so current always get distributed according to the resistance connected in parallel combination. So if all resistance are same, then each resistance will have equal amount of current. So option A is right. Okay. Next is the current in other resistance, three resistances R12, R13 and R23 is 0. So if terminal 1 and 2 are short circuited, so total current will bypass resistance R12, R23 or R13. Okay, so it means they will have zero current. So option A and B are correct in this question. Question number 27. Okay. Now there is common circuit for question number 28, 29 and 23, 30. Here at diagonal resistance are connected R by 2 and R by 2, and at edges resistance are R between A, B, C, D. So choose the correct statement related to the resistance between any two points. So here we can see that this entire circuit is symmetric. So if we'll take any 2 point, any pair of points, then we'll get same resistance, right? So RAB equals to RBD equals to RBC, RCD, RA. All resistances will remain same just because of symmetry. Okay. Next, if all are same, then these two options would not be right. Next is RAB equals to RAC equals to RBC and RCD equals to RAD equals to RBD. It is again right because it is already shown in option A. Next, choose the correct diagram which shows two-dimensional equivalent tetrahedron. So, if we'll draw equivalent diagram for this combination, then we'll get all four possible figures. Okay, because there is a circuit having four terminals and two wires are crossing each other with the help of jumper wire. That is evident in all these circuits, all these equivalent diagrams. So all four options are possible. Next, if a battery is connected between any 2 points of the tetrahedron, then identify the correct statement. First, the potential of the other 2 points are always equal. Okay. So if it is symmetric and we are applying a voltage source, then current will get equally distributed, right? So potential difference would remain same. Option A is right. There always exists a branch through which there is no current. Here we can see. Let's check in this circuit. Suppose if we'll connect a voltage here, then due to symmetry, potential of point C and potential of point D would remain same. So if there is no potential difference between point C and D, then net current passing through CD would be equal to 0. So hence, due to symmetry, if we'll connect a battery between any 2 points, then there will be at least one branch in which there will be no current. Okay. Next, the current coming out of the battery in each case is the same. So if in question 28 we already determined that the net resistance across any pair of points is same, then definitely will connect battery between 2 points, then they will offer same amount of current. So option A, B and C all are right here. Now, this question is very interesting, that it seems like a balanced Wheatstone bridge, but in place of load resistance, there is 8-volt battery connected across terminal VD and 12-volt battery connected across terminal AC. Okay. So So we can directly answer question number 31, then we'll perform further analysis. Question number 31 is, identify correct statement. The circuit satisfied the condition of balanced Wheatstone bridge. So basically in balanced Wheatstone bridge, there must be no current passing through at least one diagonal where load is connected. Okay, but in this case at both diagonals a battery is connected, then there is possibility of current between these terminals. So statement 1 is not right. Next, potential difference between point P and point D. So if we are connecting a fixed energy source or battery of 8 volt between terminal V and D, hence potential difference would remain same, that is equals to 8. So option C is correct on question number 31. Now between question 32 and 30, question number 32 and 33, we have to perform analysis. So let's look at this. Okay. Let me again look at the circuit. Between terminal A and C, there is 12 volt. All are 4 ohm resistance. There is 8 volt between terminal B and terminal D. Okay. Now please, if we assume that current I is coming out from cell of 12 volt and current I1 is from here and I2 in this range, and suppose this cell is delivering current I3, then according to KCL, current in this resistance would be I1 plus I3. On the other hand, current in this branch would be I2 minus I3. And finally again we'll get same current I, which is equals to I1 plus I2. Right. So if we write KVL equation in this branch and KVL equation here and one KVL equation outside. So for first loop we can write 4I1 minus 8 plus 8 minus 4I2 is equals to 0. Or we can say that 4I2 minus I1 is equals to 0. It means equals to 8. It means I2 minus I1 is equals to 2 ampere. This is first equation for loop number 1. Similarly, we can write equation for loop 2. In loop 2, this is 8 minus 4 I1 plus I3, right, plus 4 I2 minus I3, which is equals to 0. So from here we'll get I1 minus I2 plus 2 I3 is equals to 2, right? And from this equation we can see equation number 1. I2 minus I1 is 2. So we can replace this I1 minus I2 by minus 2. So minus 2 plus 2 I3 is equals to 2. So from here we'll get current I3 is equals to 2 ampere. Okay. Now if we'll write equation in loop number 3. So in loop number 3 12 minus 4i2 minus 4i2 minus i3 is equals to 0. Now we already have value of i3. So we can write 12 minus 8i2 plus 8 is equals to 0. Here we are substituting i3 equals to 2 amps. So from here we'll get i2 equals to 2.5. Okay. From equation 1, i2 minus i1 is equals to 2. So we may write i1 is equals to 0.5. Okay. So now we can mention all the current from this calculation in given figure. That this current is 2 ampere. Okay. Current in this branch is 2.5 ampere current I1. In this branch current is 2 ampere. Okay. And again if we'll check, this is I1 plus I3. I1 is 2.5 and I3 is, okay, once again, I1 is 0.5 and I1 is 2.5. So from here we will get 3 ampere current in this branch. Okay. And 2.5 again here. And net current is 3 ampere. I think I am committing some mistake. Let me write it again. Current I1 we have got 0.5, right? So it means current in this branch is 0.5. Current in this branch is 2 ampere. So definitely here we'll get 2.5 ampere. Again, in this branch we already calculated 2.5 and here we'll get 0.5 ampere. So net current coming from 12 volt cell is 3 ampere. So question number 32 is, which of two batteries is getting charged? So here we can see both cells are delivering current. So no charging process is taking place. So option C is right, that none of these is correct. Now next is choose the correct statement. The current coming out of 8 volt battery is 2 ampere. It is right. Next, the current coming out of 12 volt battery is 3 ampere. Again, it is correct. The current flowing in all 4 branches is same. It is not right. Next is the current flowing in diagonally opposite branches is same. So here we can see between A, B and DC. Current is same, 0.5 ampere. And in AD and BC, current is same, that is 2.5 ampere. So this option is correct. So in this question